Hey everybody, Evan again with a new video. Today we'll be talking about this is today we'll be creating a new distillation column, kind of like the first video we had. But this time we will be incorporating a hold up. So we will have liquid hold up in our distillation column that will change our vapor dynamics and our liquid dynamics. So it'll be a little bit different, more challenging for sure, especially for our Python code, but we'll figure it out together. So for our constraints, so I'll read off our prompt statement. So we are supposed to derive a differential equation governing a rate of change in liquid molar holdup and mole fraction of the more volatile component in the distillation column. Assume constant molar flow rates of each section, rectifying and stripping. Negligible vapor dynamics and vapor flow to condenser is perfect controlled to match the sum of the reflux and distillate flow. The liquid flow rates can be assumed to follow Weir's equation, where holdup is the holdup at which no liquid overflows the Weir at each stage. And then this ignores the typical considerable bubble volume entering the liquid. Okay, that was kind of a lot, but I'll break it down. So, like I kind of said, we have our conditions is one, we have constant molar flow rate. So we have constant molar flow through a distillation column. Second one, we have negligible vapor dynamics. So this could be a case of one, the heat, the energy, the heat energy of the vapor density is extremely larger than the energy of the liquid density. So it's even with the change of a liquid, our liquid or our liquid or our vapor in our distillation column, it would be negligible because how big the difference is between heat energy, because of the heat energy of our distillation column. And then second reason is that kind of like I just said, the density. We know that if we change the liquid density, and if it comes out of our density or liquid and vapor, we know that the vapor density is much smaller than the liquid density. So even by changing the liquid densities, increasing density of our vapor, it still doesn't really change the effect in our distillation column because how different is the negative, how small the difference is from changing the density of our vapor. So that could be the reasons. For our next condition, we have VLE, so vapor liquid equilibrium, which we talked about earlier in our first video we did when we designed our first distillation column. And we'll discuss this more in our Python code. And then next we know that the condenser is perfectly controlled. This means that all the vapor going in is perfectly controlled and is perfectly, all the vapor going in is being perfectly controlled and being condensed into liquid. Pretty much sums it up. And then the flow rates follow Francis-Weir formula. Okay, and then Francis-Weir formula, it's a new basically a new topic that we're covering today. And basically all it is, first, what is a weir? A weir is basically in our distillation column. When you look inside the stages, we have our stage here. This is we represent like a stage. We have this section right here that would be considered the weir, where it builds up liquid as flow comes down from the stage prior, so liquid keeps building up until we have an overflow, which is where we're getting the hold up from. So let's say, and I'll explain this more, we could draw my full distillation column diagram. We have a flow of liquid from this point in our stage. We have our weir at this height. This is all liquid, okay? So we have the height of the weir, and then we have the height that is built up from our hold up from the weir being there. So we have the total liquid, and then we have the area of the weir, area of the hold up due to the weir, and then the height of the difference. Okay, and this is how it's literally represented in our equation. So the equations for instance, weir, is literally the flow rate, the flow of liquid is equal to the height of the weir times the moles of the total liquid minus the moles of the holdup. Okay. And then this to be factored, this to be on the coefficient of 1.5, okay? So that's basically what Francis' weird formula is. Yeah. So now we have the basis of that. Let's actually draw our full distillation column, and we can start working out our mass balances for each stages, the condenser and the reboiler, and how it'll look like. Sorry about the pause. My computer was about to die. But yeah, let's draw out our distillation column now. I'm gonna erase this for now, but it's gonna get redrawn later, so it's okay. So in our distillation column, let's just have stages, condenser. We have the big stage. Ooh, we have a reboiler. And as we know, let's say a feed is going into stage N. This is N minus one, stage above, N plus one, stage below. Should be total amount, so N, initial 0. So we have our feed. We have our distillate. And then we have our bottoms. And then we have the liquid and vapors coming in and out of all stages. Okay. So like I just mentioned, if we focus on stage N, we redraw out the weir, and we go deeper, we actually just like going into the distillation column. We draw our weir. All right. Weir on the flow. And then this. Okay. Like I just mentioned, we have our weir, has a height, has initial height, and then has the height of the hold up. Okay. We know that there's a liquid coming down from stage Ln minus one from the previous weir. Okay. From the distillation column. That gets flowed down. We know that there's vapor coming up from the bottom stage. Now be vapor of N plus one, and then we have the bubbles inside the liquid, showing the vapor passing through the liquid. We have a vapor going up to the next stage, which would be V of N, and then the liquid leaving from the stage to the next weir. Next stage, it's L of N. Okay. So the biggest problem with this is really just figuring out what will be our mass balance for just the in-between stages for this holdup. Which is if you really break this down, it's actually not that bad. So let's start with just a general mass balance for the stage. So we have a mass balance. We know lesser is going in. So for liquid side, we know that going in, we have the liquid at the stage above. So that's a liquid at N minus one minus the liquid leaving. So the current stage of Ln plus the vapor coming in. So at V at N plus one minus the vapor leaving, which is the vapor at current stage, so minus V of N. Okay. And then we also have a mole bounce. So, and this will be, I forgot, I keep forgetting to do this. I'll just do it on this side. It would be respect to D at our moles, the Mn, moles at stage N, expected time, so D of Mn. Then we have our mole balance mole balance, which would be, now I'll put this in the front, but the difference in the moles of N times the liquid liquid species of N divided by dt. And this is equal to, now we're just putting the liquid or vapor species for each of the phases. So this would be x of n plus n minus 1, L of n minus 1, minus L of x of n, L of n plus the vapor at the at n plus 1 stage below, and times the vapor at stage below, minus the vapor current stage times the vapor flow rate. No, sorry. So yeah, this is the vapor flow rate. This is the liquid vapor flow rate mass balance, and then this is the mole balance. So we have our change in the species flow rate times its species. So we have liquid, the liquid composition times the liquid flow rate stage above minus the liquid composition times the liquid flow rate at our current stage plus our vapor coefficient, or vapor composition times our vapor flow rate of the stage below minus the vapor composition times the vapor at our current stage. Okay, so if you see the problem, the problem we have here is that we have a term for our initial is the change of our the change of our our material flow rate times our species is currently combined together. We want these terms isolated because we want, for our mole balance, we just want dx of n of dt. We don't want to have the mole flow rate in that difference as well. So we have to do a product rule for this. Okay? So here are the product rules. If you Q, it is, I'll do an example. We say we had the derivative of xy respect to divided by derivative of t. This would be equal to, we do x times derivative of y divided by derivative of t plus y times derivative of x times the derivative of t. Okay, so that's how product rule is. So we would do it for this function right here. So let's do it. So this would be d mn xn over dt is equal to mn of dxn dt plus xn of dmn dt. Okay. So now we have our isolated terms for both of them. Of course, we want to put xn on the other side, so we can do that now. So we can do dxn of dt is equal to 1 mn parentheses, and then there's be these two inside, so we have d of mn xn divided by dt minus xn of dm of n of dt. Okay. So if you figure it out, we can actually plug in, because we actually the derivative of our flow rate selected time. Here we have this function. This function is actually stated up here in our mass balance. Okay, you're not putting on the wrong side. It's actually represented up here in our mass balance. So we can actually just resubstitute this as balance in for our mole balance, and just plug that in. And we also already have the function for our mole balance, our initial mole balance. So we have before we did the product rule. So we can actually plug in both of these expressions into here, and then we'll have our mole balance for our expression. So let's do that real quick. It's gonna be a long expression, but it'll be, I'll just write this out. So dxn a dt, and then both of our expressions, so it's equal to 1, and then the long part, so we got minus 1 1 6 plus y plus 1 plus 1 minus x and this expression now. Oh, minus 1 this plus plus 1 minus b. All right. Okay, so now we have our two expressions. So now we have our mass balance and we have our mole balance. Okay, so that's all we need. And then, mind you, this is literally just for our in-between stages. Okay, this is not for our reboiler and condenser yet. We're about to get to that. Those two are kind of special a little bit because we have to factor in the condenser and reboiler. So our bottoms and our distillate. So we'll do that now. And obviously I'll just do that right here because we don't have a lot of space left. So if we're gonna do our reboiler first, so add our reboiler. This would be mass balance for first, so it'd be E of Mn dt. And actually, we already know from our conditions given, or initially, we know that our condition is perfectly controlled. So when we have a statement that says perfectly controlled, we know that our flow rate would just be equal to 0. Because we know when we set up our mass balance, this is be our initial mass balance is be V n minus 1 is equal to liquid at say 0 plus distillate. Okay. And we know that these two terms, the sum of these two is really just equal to this. So we know that Vn minus 1 minus L, the vapor coming in minus the liquid at the stage plus the distillate, that is equal to our vapor flow. There's no like air, there's no like what's the word I can say? Because the condenser is perfectly controlled, we will have a perfect ratio from our vapor fully get condensed simultaneously with the liquid and distillate. So when we put this in, this would be this expression right here. So it'd be Vn plus 1 minus L plus D. Okay, and it's the exact same thing for if we do a mass mole balance, Vd Mn Xn dt is equal to 0. So this will also be equal to 0, and then we just plug in the water vapor. So it'd be y Vn minus 1 minus X LO plus XD E minus XD D. All right. That's the case for the reboiler. We already know it's equal to 0 because it's perfect control. But for the reboiler, oh, I'm sorry. I said the wrong case. This is for the condenser. Yeah, my bad. This is for the condenser. I think you probably caught up on that when I started making the conditions, but for the reboiler, our case is different. Our reboiler is not perfectly controlled at the moment. Definitely over time, once the distillation column reaches steady state, it will become perfectly controlled. But at the when we first started off, it would not be perfectly controlled, and this is due to the vapor and liquid dynamics of our distillation columns from the holdups. So what our reboiler will look like is kind of the same case for like our condenser. Would be the same thing, d of n or dt. Instead of it equaling to 0, it is equal to the regular mass balance, which we know is just our liquid coming down from all the stages. So from n plus 1. Well, no, it'll be n minus 1 in this case. Oh, and this would be n plus 1. I'm sorry. I just repeat that. It is v plus 1 here. Liquid from the top stage is equal to the vapor at stage N plus the bottoms. Okay, so then we move this to this side, and then we would just get the liquid coming down minus vapor of the stage minus the bottoms, and then we move the mole balance. Then we just plug in the harder liquid composition. So x of n minus 1 minus y. Oh, oh minus y and bn minus x b b. Okay. So that's it, ladies and gentlemen. We have now our mole balance and mass balance for all the stages that would be desired in a distillation column. And for the condenser and reboiler, we can now put this into Python and we can run this, and you can see how it will look simulated. And also, what I want to note is that if we added our feed, because we in this situation there was no feed added, but in our actual implications there will be, keep dropping my marker. But there will be feed added. So we just add feed. Literally, all we would do is like for our mass balance for the stage of N, all we would do is add F. So at the end, we just do plus F here. So in our balance, we just do plus F would be added. I don't know if you can see, you still can't see it all. But we'll just add the feed, and then for our mass balance, we just more balance with Z times CF of Z times F. That's all we'll do. And it'll work out in our big expression. But yeah. That's it. Sorry, someone came in. That's it. And I will see you guys on the next video.